So that's how we calculate a p-value, both for a completely randomized design where we draw names out of a hat and a Bernoulli randomized design where we think about flipping a coin. But either way, the idea is that if you know how the randomization went, if you know how people were allocated to one group versus another, you can go through this process and calculate the p-value. Let's look at the slides. So here we have the slide that we left off on where we show our pretend data set that we were just working with. Here's what we got when we actually used all 207 people and took into account the Bernoulli randomization. The histogram that we're showing here represents the difference in means that we'd expect to see under all possible ways to allocate some people to an HLAB offer and some people not to an HLAB offer, assuming that the HLAB offer had no effect. And the red line here, the red line indicates the difference in means we actually saw. Remember, the difference we actually saw was 76% minus 72%. It was a 4 percentage point difference. So what's the probability we would have seen a difference in means at least this big if actually there was nothing going on, if actually the HLAB offer had no effect? The answer is 0.26. 0.26. A quarter of the time, we'd see a difference, at least as big as we actually saw, if the truth is that HLAB had no effect whatsoever. We do not have evidence to reject the null hypothesis that an offer of HLAB help doesn't change the win rate whatsoever. And this is based on Bernoulli randomization. So to formalize some of what we're saying so that you have it for notes, the null hypothesis is an assumption that specifies a possible truth. And typically we choose as the null hypothesis the assumption that there's nothing going on. Here I've written the absence of an effect or a difference. Another way to think of it is as a statement of old beliefs. There's no change, no difference, no effect. The null hypothesis is that there's nothing going on here, even if you're trying to prove the opposite. The alternative hypothesis is anything else. We have a null hypothesis, and if the null hypothesis isn't true, the alternative hypothesis is true. There's some effect, there's some difference. New belief might be the truth. And let's continue giving you some definitions, even though we've already been using them. A statistic is a numeric quantity that can be calculated from the data you actually observed. And a test statistic is a statistic that we use in a test, a statistic that's used to weigh evidence supporting versus contradicting the null hypothesis. The reference distribution is the probability distribution of the test statistic, exactly what we've been showing you in these histograms. Assuming that the null hypothesis is true, what is the probability of each value of the test statistic? And then we calculate our p-value. And here's a lot of words, but you've already seen how to do this using the histograms. The p-value is the probability that the test statistic would be at least as extreme as actually observed when the null hypothesis is true. It's what we get when we compare the test statistic to its reference distribution. We'll come back to this, but note that the p-value is not the probability that the null hypothesis is true. Again, sometimes it's easiest to think about the p-value in terms of what it's not. The p-value is not the probability that the null hypothesis is true. Rather, the p-value is, assuming that there's nothing going on, what's the probability we'd see data at least as surprising as we actually saw? Assuming that HLAB has no effect on whether people win their cases, what's the probability we'd see a difference in win rates of at least 4 percentage points? Assuming that the lady has no ability to tell the difference between milk first and tea first, what's the probability she'd still get at least 3 cups right? Is that likely to happen by chance, or do we have evidence contradicting the null? That's what a p-value actually is. And just so you have these definitions, the left-sided p-value is the probability that we'd see something at least as small as actually observed. The right-sided p-value is the probability we'd see something at least as high as actually observed. The one-sided p-value is just the minimum of those two. In other words, what's the probability we'd see something at least as far off to the side as actually observed? And by definition, the two-sided p-value is 2 times the one-sided p-value. Sometimes I hear people talking a lot about whether they should be using a one-sided or a two-sided p-value in a particular context. The truth is that if you give me a one-sided p-value, I can double it and tell you the two-sided p-value. If you give me a two-sided p-value, I can half it and give you the one-sided p-value. As long as you give me a p-value and tell me which one it is, one-sided or two-sided, I'm going to have all the information I need. So it's not worth stressing about which one of these you want to present. Rather, present the one that you think is more useful. And make sure you say which one it is.